Moore's Law is a name that was given to a projection I made actually in 1965. I was given the chore of predicting what would happen in semiconductor components over the next 10 years for the 35th anniversary edition of Electronics Magazine. That was the early day of integrated circuits. The most complicated ones on the market had something of the order of 30 transistors and resistors. We were working on things of about twice that complexity, about 60 components. And I just plotted these on a piece of semi-log paper and noticed that since the first planar transistor was introduced in 1959, with integrated circuits following essentially on the same technology, that the number of components on an integrated circuit was about doubling every year. I wanted to make the point that integrated circuits were going to be the cheap way to buy electronics sometime down the road. Up until 1965, integrated circuits were expensive. They were used principally in military systems where the weight and power advantages were most important. But they were not inexpensive compared with what you could build using separate transistors and resistors. I could see at that time that the way the technology was going, that we were going to be able to decrease the cost dramatically. So I did this 10-year extrapolation, doubling every year, predicting the complexity of integrated circuits would be 1,000 times as complex in 1975 as it was in 1965. That is, we'd have of the order of 60,000 transistors on an integrated circuit instead of just 60. And that this would be the cheapest way to buy electronics.
Moore's Law states that transistor density will double every 2 years on integrated circuits, as represented here on a linear scale. Carried out over a 10-year path, that growth can be charted in this manner. On a logarithmic scale, as done by Moore in 1965, the rate of growth is represented as a straight line. This is an exponential growth, and when viewed over a 40-year period, what has occurred is a million-fold increase in density, with the bulk of that growth occurring in the past decade alone.
Now, while I was sure of the trend, I had no idea at all that the prediction would be in any respect accurate. But amazingly, we stayed on that curve for the first decade. And one of my friends, I believe it was Dr. Carver Mead, a professor at Caltech, dubbed it Moore's Law someplace along that time scale. I don't remember exactly when, but that's how Moore's Law came about.
The whole nature of that curve as being some sort of law is a very interesting phenomenon, because it's not a phenomenon like a law of physics. It's really a phenomenon about what people are willing to let themselves believe. And what it did is it gave people a confidence to go take the next step. And after a while, those things become self-fulfilling because people can believe that they can do it. So they go off and do what's necessary to make it come true. And that's really what happened with Moore's Law. It's really that Gordon gave people permission to believe in the future, and they went off and made it happen.
I used to be kind of embarrassed. I'd cringe when I heard people call it Moore's Law. But I've heard it enough over the last 20 years or so that I've gotten used to it, so now I can say it with a completely straight face. Of course, there's nothing associated with it that's really a physical law. It's just the rate at which the technology was evolving.
And that rate carried Moore's Law into many other areas of the industry.
I guess I was the first one to plot some of these exponential changes in the industry. And now almost anything related to the industry that changes exponentially is called Moore's Law, and I'm happy to take credit for all of it. In fact, I say if Gore invented the internet, I invented the exponential.
Those of us in the industry who were in the working trenches then, we were pretty young. And there's this great guy who's been around all through the history of integrated circuit industry, drawing a line and says this is where the appropriate transistor density is going to be. So our people were designing integrated circuits with that line in mind. That was the target. Then the technologists and the fabrication people were designing processes to build the circuits that embodied the transistor count in Moore's Law. So maybe it became a self-fulfilling prophecy. And I don't think we can ever tell the difference.
And of course, we didn't stay on that doubling every year. In fact, in 1975, updating the progress we had made, I gave a paper at one of the IEEE conferences where I predicted that the slope was going to change to doubling every 2 years, since we had lost one of the big factors. We hadn't lost it, we had taken full advantage of it. There wasn't any more room to pack things more densely on the chip unless we made them smaller. So I said we were going to lose that factor, and subsequently it about double every 2 years.
But somehow along the line, that 2-year projection got reduced to 18 months.
I never understood until recently where the 18 months came from, since it was nothing I had ever said. I figured somebody else replotted the data and figured that was better. But in talking to a former Intel employee, Dave House, he described the origin as plotting the increase in computer performance. And his view was the computer performance was increasing by the increase in complexity, so it was doubling every 2 years from that. And in addition, the clock frequencies were going up, so the combination gave you an increase in computer performance, doubling about every 18 months. One thing that has happened here is these exponentials that are lumped together as Moore's law have become, in a real respect, a self-fulfilling prophecy. The participants in the industry all know these trends. In fact, the technology roadmap that the Semiconductor Industry Association turns out has these exponentials plotted in it. And all the companies realize that unless they move at that rate, they fall behind the rest of the industry. So there's a tremendous amount of pressure to stay on the curve or to get ahead of it.
You know, if you weren't following Moore's law, you were following behind other people in the industry. And that competitive issue, I think, has made the entire industry work harder, plan farther ahead, invest more money. And the end result of all that was just to bring a tremendous amount of technology to the end user. There's been a real microelectronics revolution, the computer revolution.
And now it's accelerating a little bit. Intel has cut the time between process generations from 3 years to 2 over the last few generations. And our competitors are trying to keep up with that. So there's a race to stay ahead, and it's because we're all looking at these same curves of how fast things evolve. A peculiar thing about this technology is that the new technology, the one with the smaller structures, not only makes higher performance devices and one thing and another, it also makes them cheaper because they occupy less area. So anybody that has the new technology, is a generation ahead of his competitors, has a tremendous cost advantage over the competitors. So no one wants to be put in the position of being a generation behind.
So the question arises, what limits the continuation of Moore's law?
No physical thing can continue to change exponentially forever. The nature of the exponential, it grows so big or so small so rapidly that you come to some kind of a physical limit. Even in our present technology, some of the layers are only a few molecular layers thick. But as we approach the atomic dimensions, the materials don't behave the same way anymore. We get a lot of new leakage currents coming in, standard circuit design doesn't work, and eventually we really come across something fundamental, that there's a size below which the electronic functions don't work. Something below 1/10 of a micron, probably 0.05 microns, looks like it's getting very close to that limit. Now 0.05 microns is about 3 generations of technology away from the 0.13 that we're currently developing. And given the usual time for a generation of a few years, that gives us something of the order of 10 years from where we are before we can't go any further in what we're doing in the technology. So sometime between 2010 and 2020, I think we're going to be up against this physical limit that making things smaller doesn't help anymore. But that is not really the end of Moore's law. Now, it may change the slope, because a very important part of being able to make more complex and faster devices has been making things smaller. But it's not the only thing. Even with the limit we have then, we'll be putting 1 billion transistors on a logic chip. With a budget of 1 billion transistors, our engineers will have phenomenal ability to innovate. Almost anything they can think of can be realized in that complexity. So it's not the end of progress in the industry. Maybe I've just gotten old and set in my ways, but I don't think the question of what after silicon is the right question. I don't see anything taking the place of what we've done with the integrated circuit technology. We may change some of the materials. I doubt we do in the mainstream, but we may use a different semiconductor. But I think that the technology we've developed, this building a complex pile of materials with a complex microstructure, layer by layer, by depositions and etchings, is a fundamental technology for making microstructures. And rather than that being replaced by something else, it's more nearly going the other way. That is finding its way into several other fields.
The laws of physics are not breakable, so evolution of semiconductor technology will continue, but it will have to take steps that make it go on in spite of the limitations that physics imposes on it or skirting them. And I think it will do that. I'm confident it will do that, but it's going to require pretty original out-of-the-box thinking on the part of technologists and device designers.
We can see how to continue this behavior for at least another 10 or 15 years. And that's just using the standard CMOS transistor. It's going to be difficult. It's going to just take a fantastic amount of intense engineering effort, hundreds of millions of dollars of research, developing new lithography tools, new etching tools, new circuit designs. But it can be done.
There's a long way to go before we've run out the string of what we can do with solid-state electronics.